The universe stretches before us, vast and infinite, filled with more stars than grains of sand on all the beaches of Earth. Yet in this cosmic ocean, we find ourselves on a small blue world, orbiting an ordinary yellow star. When we look up at the night sky, the points of light we see are our neighbors in this grand celestial neighborhood. Tonight, we embark on a journey to visit our closest stellar companions, the stars that share our corner of the Milky Way galaxy. For thousands of years, humanity has gazed upward, wondering about those distant lights. Ancient civilizations wove stories around them, navigating by their positions, marking the passage of seasons through their movements across the sky. But it wasn't until recent centuries that we began to understand what stars truly are, and even more recently, that we've been able to measure the distances to our nearest neighbors with precision. The nearest stars to our Sun lie in what astronomers call our local stellar neighborhood. These are the stars within roughly 10 to 12 light-years of our solar system. To put this in perspective, a light-year is the distance light travels in 1 year, moving at an astounding 186,282 miles per second. That's nearly 6 trillion miles for a single light-year. Even our closest stellar neighbor is separated from us by a gulf of space so vast that it challenges our comprehension. Yet these nearby stars are, in cosmic terms, right next door. The Milky Way galaxy spans about 100,000 light-years from edge to edge and contains between 200 and 400 billion stars. Our neighborhood represents the tiniest fraction of this immense stellar city. If we imagine the galaxy as a vast metropolis, our local stellar neighborhood would be like a single city block, with our Sun as just one house among many. These nearby stars come in a fascinating variety. Some burn with intense heat and brilliant light, while others glow dimly in the infrared, barely visible to our telescopes. Some are ancient wanderers that have traveled through the galaxy for billions of years, while others are relative youngsters in stellar terms. Some host planets of their own, possibly worlds, where conditions might allow life to emerge and evolve. Each star has its own story, its own character, its own place in the cosmic dance. The technology that allows us to study these stars has advanced dramatically in recent years. Space telescopes orbit above Earth's distorting atmosphere, capturing light that has traveled for years across the void. Ground-based observatories, equipped with adaptive optics, can now peer through the atmosphere with unprecedented clarity. Spectroscopy allows us to analyze the light from distant stars, revealing their composition, temperature, motion, and even the presence of planets. We live in a golden age of stellar astronomy, where discoveries come rapidly and our understanding deepens with each passing year. As we journey to each of these stellar neighbors tonight, we'll discover worlds both familiar and alien. We'll encounter stars that dwarf our Sun and others that barely qualify as stars at all. We'll visit systems where multiple stars orbit each other in an endless cosmic ballet, and solitary stars that drift through space alone. We'll explore planets circling distant suns, considering the possibilities they present for life beyond Earth. The journey we're about to take is one of imagination informed by science. While no human has yet traveled beyond our solar system, our robotic explorers have ventured into interstellar space, and our telescopes serve as time machines, showing us light that left these stars years ago. Through careful observation and theoretical understanding, we can paint detailed pictures of these distant worlds, knowing that each photon of light that reaches us carries information across the cosmic void. Consider for a moment the photons entering your eyes as you gaze at a nearby star. Those particles of light began their journey years ago, escaping from the surface of a star in a random direction. They traveled through the perfect vacuum of space, perhaps passing through clouds of interstellar dust, maintaining their course across trillions of miles, only to end their journey by striking your retina and allowing you to perceive their distant source. You are literally seeing into the past, observing these stars not as they are now, but as they were when that light began its journey. Our exploration tonight will take us to 10 of the nearest star systems to our Sun. We'll begin with our absolute closest neighbor and work our way outward through our immediate cosmic vicinity. Each star we visit represents a different chapter in the story of stellar formation and evolution. Each offers unique insights into the diversity of stars in our galaxy and the potential for planets and life beyond our solar system. The distances we'll discuss may seem incomprehensible at first. When we speak of a star being 4 or 8 or 10 light-years away, these numbers can feel abstract. But consider this perspective: the fastest spacecraft humanity has ever built, the Parker Solar Probe, reaches speeds of about 430,000 miles per hour at its fastest. At that speed, it would still take over 6,000 years to reach our nearest stellar neighbor. The distances between stars are truly vast, a reminder of both the scale of the universe and the impressive achievement represented by our ability to study these distant objects at all. Yet despite these vast distances, we are connected to these stars in profound ways. The atoms that make up our bodies, the oxygen we breathe, the carbon in our cells, the iron in our blood, all were forged in the hearts of ancient stars that lived and died before our Sun was born. We are, quite literally, made of stardust. Every star we'll visit tonight is engaged in the same fundamental process that created the elements necessary for life, fusing lighter elements into heavier ones, enriching the galaxy with the building blocks of planets and living things. As you settle in for this journey, allow yourself to relax and let your imagination carry you across the light years. Picture the darkness of space, punctuated by the glow of distant stars. Feel the timelessness of the cosmos, where stars burn for billions of years and galaxies slowly wheel through space. Let the gentle rhythm of our exploration carry you along as we visit each stellar neighbor in turn. The universe is patient and eternal. The stars we'll visit tonight have been shining for millions or billions of years, and most will continue to shine long after humanity has either spread among them or passed from existence. They represent something larger than ourselves, a cosmic context that puts our brief lives in perspective. Yet they also represent possibility, the chance that we are not alone, that among the planets circling distant suns, life may have found a way to emerge and flourish. Our journey begins now, as we travel to the very edge of our solar system and prepare to take that first great leap into interstellar space toward our closest stellar neighbor. The adventure awaits. Our first destination lies just beyond the edge of our solar system, across a gulf of 4.24 light-years. This is Proxima Centauri, the closest star to our Sun, our nearest neighbor in the vast darkness of space. The name Proxima comes from the Latin word for nearest, a fitting designation for this small red star that holds the distinction of being our closest stellar companion. Proxima Centauri is a red dwarf star, the most common type of star in our galaxy. It's significantly smaller than our Sun, with only about 12% of the Sun's mass and about 1/7 of the Sun's diameter. If you could place Proxima Centauri beside our Sun, it would look like a small red ember next to a brilliant yellow flame. Yet despite its diminutive size, Proxima Centauri is a true star, fusing hydrogen into helium in its core, generating energy through the same nuclear processes that power our Sun. The surface temperature of Proxima Centauri is about 3000 Kelvin, much cooler than our Sun's 5800 Kelvin. This cooler temperature gives the star its distinctive red color. It's also much dimmer than our Sun, producing only about 0.17% of the Sun's luminosity. In fact, despite being our closest stellar neighbor, Proxima Centauri is too faint to see with the naked eye from Earth. You would need a telescope to observe this nearby star, a humbling reminder that our perception of the universe is limited by the capabilities of our senses. Proxima Centauri belongs to the Alpha Centauri system, a triple star system that includes two larger stars, Alpha Centauri A and Alpha Centauri B, which orbit each other closely. Proxima orbits this pair at a great distance, taking more than 500,000 years to complete one orbit around them. This distant connection raises an interesting question: is Proxima truly bound to the Alpha Centauri system, or is it simply passing through? Astronomers continue to study the motion of these stars to understand their relationship. What makes Proxima Centauri particularly exciting is that it hosts at least one confirmed planet, and possibly more. Proxima Centauri B, discovered in 2016, orbits its star every 11.2 days at a distance of about 4.7 million miles. This might sound close, but remember that Proxima is much dimmer than our Sun. So this planet sits within what astronomers call the habitable zone, the region where liquid water could potentially exist on a planet's surface. Proxima Centauri B has a minimum mass about 1.3 times that of Earth, suggesting it could be a rocky world like our own. The possibility that our nearest stellar neighbor hosts a potentially habitable planet has captured the imagination of scientists and space enthusiasts alike. Could life exist on a world orbiting Proxima Centauri? We don't yet know, but the possibility is tantalizing. However, Proxima Centauri B faces significant challenges. Red dwarf stars, like Proxima, are known for producing powerful stellar flares, eruptions that release intense radiation and charged particles. These flares could potentially strip away a planet's atmosphere or bathe its surface in harmful radiation. Additionally, planets so close to their stars typically become tidally locked, meaning one side always faces the star while the other remains in permanent darkness. This could create extreme temperature differences between the star-facing and dark sides of the planet. Yet life, as we've discovered on Earth, can be remarkably resilient and adaptive. Scientists continue to study Proxima Centauri B, trying to understand its atmosphere, if it has one, and whether conditions on this world might permit life as we know it, or perhaps even life as we don't know it. Proxima Centauri is also interesting because of its longevity. Red dwarf stars burn their fuel very slowly, living for trillions of years. Our Sun, in contrast, will last for only about 10 billion years total, and it's already about halfway through its life. Proxima Centauri has likely been shining for billions of years already, and it will continue to shine long after our Sun has exhausted its fuel and died. If life exists on planets around Proxima Centauri, it would have vast amounts of time to evolve and develop. The star moves through space at a velocity relative to our Sun, and interestingly, it's currently approaching us. Over the next few thousand years, Proxima Centauri will actually get slightly closer to our solar system before beginning to move away again. It reached its closest approach to our Sun about 26,700 years ago, when it was about 4.22 light-years away, just slightly closer than it is today. Proxima Centauri represents humanity's most likely first destination for interstellar travel, whenever we develop the technology to make such journeys. Various proposals have been suggested, from generation ships that would take thousands of years to reach the system, to laser-driven light sails that might make the journey in just a few decades. The Breakthrough Starshot initiative has proposed sending tiny probe spacecraft accelerated by powerful lasers to a significant fraction of light speed, potentially reaching Proxima Centauri within 20 to 30 years of launch. As we contemplate this small red star, we're reminded of both the vastness of space and the proximity of our cosmic neighbors. Proxima Centauri is right next door in galactic terms, yet reaching it represents an almost incomprehensible challenge with our current technology. The light we see from Proxima left its surface over 4 years ago, crossing the void to bring us information about our nearest neighbor. On a dark, clear night, if you look toward the constellation Centaurus in the southern sky, You won't be able to see Proxima Centauri with your naked eyes, but you'll know it's there, a small red coal glowing in the darkness, possibly hosting worlds where alien landscapes stretch beneath a dim red sun. It's a humbling and inspiring thought, this nearest of all stars, both impossibly distant and yet somehow within reach of our future ambitions. Just slightly farther than Proxima Centauri, at a distance of 4.37 light-years, we find Alpha Centauri A and B, a binary star system where two sun-like stars orbit each other in a cosmic dance that has continued for billions of years. These stars are not only our close neighbors, but also among the most interesting stellar pairs in our galactic vicinity, offering us a glimpse of what a double star system looks like up close. Alpha Centauri A is remarkably similar to our own Sun. It's a yellow G-type star, only about 10% more massive than the Sun, and roughly 22% brighter. Its surface temperature is about 5,800 Kelvin, essentially identical to our Sun's temperature. If you could transport Earth to orbit Alpha Centauri A, at the same distance we orbit our Sun, you would barely notice the difference in the light and warmth you received. The sky would look almost the same, the seasons would progress in familiar patterns, and life would continue much as it does under our own yellow star. Alpha Centauri B is somewhat smaller and cooler, an orange K-type star with about 90% of the Sun's mass and roughly 50% of its luminosity. Its surface temperature is approximately 5,200 Kelvin, giving it a slightly orange tint compared to its yellow companion. Despite being dimmer than Alpha Centauri AE, it's still a substantial star, far larger and brighter than the red dwarf Proxima Centauri we just visited. These two stars orbit each other at an average distance of about 23 astronomical units, where 1 astronomical unit is the distance from Earth to the Sun. To put this in perspective, their average separation is roughly the distance from our Sun to the planet Uranus. However, their orbit is quite elliptical, meaning they sometimes come as close as 11 astronomical units and sometimes drift as far apart as 36 astronomical units. This orbital dance takes about 80 years to complete, a human lifetime spent in celestial waltz. From a planet orbiting one of these stars, the view would be spectacular. Imagine standing on a world circling Alpha Centauri A. For much of the year, Alpha Centauri B would appear as an intensely bright orange star, far brighter than any star in Earth's night sky, bright enough to cast shadows and provide measurable warmth. During the closest approach of the two stars, Alpha Centauri B would appear roughly the same size as a large moon, a small disk rather than a point of light. As the stars orbited each other over the decades, this companion sun would grow brighter and dimmer, closer and more distant, adding a unique complexity to the celestial mechanics of any planet in this system. Could planets exist in such a system? Astronomers have debated this question extensively. The gravitational interaction between two stars can disrupt planet formation, but it doesn't prevent it entirely. Planets could potentially exist in two configurations: close orbits around one star or the other, where that star's gravity dominates, or in very distant orbits circling both stars together, far beyond the region where the two stars' gravitational influences compete. There have been tentative detections of possible planets in the Alpha Centauri system, though none have been definitively confirmed with complete certainty. The search continues as astronomers use ever more sophisticated techniques to look for the subtle signatures of planets around these nearby stars. Given the right conditions, planets around either Alpha Centauri A or B could potentially harbor life, offering the tantalizing possibility that our nearest sun-like neighbors might also be home to living worlds. The Alpha Centauri system is relatively young in stellar terms, estimated to be between 4 and 6 billion years old, roughly the same age as our own Sun. This means that if planets formed around these stars, they've had sufficient time for life to potentially emerge and evolve. On Earth, life appeared within the first billion years after our planet formed, suggesting that if conditions are right, life might be a fairly quick development in a planet's history. Both Alpha Centauri A and B will live for several billion years more before exhausting their hydrogen fuel. Alpha Centauri AE, being slightly larger, will exhaust its fuel somewhat sooner, perhaps in another 5 billion years. Alpha Centauri B, burning its fuel more slowly, will last longer. When these stars eventually die, they will expand into red giants, potentially consuming any inner planets, before finally shedding their outer layers and leaving behind white dwarf stars, dense stellar remnants that will cool slowly over trillions of years. The system moves through space as a unit, traveling at about 22 kilometers per second relative to our Sun. Interestingly, the entire Alpha Centauri system is currently approaching our solar system and will continue to do so for the next several thousand years, reaching its closest point in about 28,000 years, when it will be approximately 3.26 light-years away. After that, it will begin to recede, eventually drifting far from our neighborhood over hundreds of thousands of years. To observers on Earth, Alpha Centauri appears as the third brightest star in the night sky, though it's only visible from the southern hemisphere and tropical regions. Ancient observers couldn't distinguish Alpha Centauri A and B as separate stars, as they appear too close together for the naked eye to resolve. Only with telescopes did astronomers discover that this bright point of light was actually two stars orbiting each other. The name Alpha Centauri comes from its designation as the brightest star in the constellation Centaurus, the Centaur. Ancient Greek astronomers imagined this constellation as representing Chiron, the wise centaur, who tutored many heroes. The ancient indigenous peoples of Australia also had stories about these stars, incorporating them into their rich astronomical traditions that stretch back tens of thousands of years. For humanity's future in space, Alpha Centauri represents a compelling destination. Two sun-like stars, close together in cosmic terms, potentially hosting planets, offering the possibility of worlds where liquid water might exist and life might flourish. Any interstellar mission to Proxima Centauri would likely also study the Alpha Centauri system, as all three stars are bound together in a single stellar family. As we imagine this binary system, we're reminded that our Sun is somewhat unusual in being a solitary star. Most stars in our galaxy are members of binary or multiple star systems, orbiting with stellar companions. Alpha Centauri A and B show us what the majority of stellar systems look like: two stars bound by gravity, spinning around their common center of mass, sharing the same corner of space for billions of years. They are partners in the cosmic dance, companions on the long journey through the galaxy, lighting each other's way through the darkness of space. Traveling outward from the Alpha Centauri system, our next destination lies nearly 6 light-years from Earth. Barnard star, a solitary red dwarf, drifts through space alone, the fastest-moving star visible from our perspective, racing across the sky at a speed that has captured the attention of astronomers for over a century. Barnard star sits 5.96 light-years from our solar system, making it the fourth closest star system to Earth and the second closest individual star after the Alpha Centauri triple system. It's located in the constellation Ophiuchus, the Serpent Bearer, and like Proxima Centauri, it's too faint to see with the naked eye, despite being relatively nearby. You would need a modest telescope to observe this stellar wanderer, a dim red point of light, making its rapid journey across the stellar background. What makes Barnard star particularly fascinating is its proper motion, the term astronomers use to describe a star's apparent movement across the sky as viewed from Earth. Barnard star has the largest proper motion of any known star, moving across our sky at a rate of about 10.3 arcseconds per year. This might sound like a tiny amount, and it is, but in astronomical terms, it's remarkable. Over a human lifetime, Barnard's star moves about the diameter of the full moon across the sky. Over 180 years, it travels a distance equal to the apparent diameter of the moon. This rapid motion doesn't mean Barnard's star is traveling faster than other stars in an absolute sense. Rather, it's a combination of the star's actual velocity through space and its proximity to us. Stars farther away can be moving just as fast, but appear to move more slowly because of their greater distance, just as a distant airplane appears to crawl across the sky while a nearby bird flashes past. Barnard's star is approaching our solar system at a velocity of about 107 kilometers per second. This approach will continue for several thousand years, with the star reaching its closest point to our Sun around 11,800 Ca, when it will be only 3.75 light-years away, briefly becoming our second nearest star after Alpha Centauri. After that closest approach, it will begin moving away, eventually leaving our immediate neighborhood entirely. As a red dwarf, Barnard's star is smaller and cooler than our Sun, with about 16% of the Sun's mass and only 14 to 20% of its diameter. Its surface temperature is approximately 3,100 Kelvin, and it emits most of its energy in the infrared portion of the spectrum rather than visible light. The star produces only about 0.4% of the Sun's luminosity, making it one of the least luminous stars visible from Earth. Barnard's star is also quite old, estimated to be between 7 and 12 billion years old, significantly older than our 4.6 billion-year-old Sun. This ancient star has been wandering through the galaxy for most of the universe's history, witnessing the formation of countless younger stars, possibly including our own Sun. It's a stellar elder, a survivor from an earlier epoch of galactic history. For decades, Barnard's star was at the center of one of astronomy's most persistent controversies. In the 1960 ES and 1970 ES, an astronomer claimed to have detected wobbles in the star's motion that suggested the presence of at least one, possibly two, planets orbiting the star. This claim generated enormous excitement, as it would have represented one of the first planetary systems discovered around another star. However, subsequent observations failed to confirm these planets, and the claimed detection was eventually attributed to systematic errors in the data analysis. Despite this disappointment, the search for planets around Barnard's star continued. In 2018, astronomers announced the detection of a candidate planet called Barnard's star B, using more modern and reliable techniques. This planet, if confirmed, would have a minimum mass about 3.2 times that of Earth and orbit its star every 233 days at a distance where surface temperatures would be extremely cold, around 170 degrees Celsius. However, this detection remains controversial, with some astronomers questioning whether the signal truly represents a planet or could be an artifact of stellar activity. The question of planets around Barnard's star remains open. Red dwarf stars are known to host planets, and given Barnard's star's proximity and the attention astronomers pay to it, any planets in this system would be among the easiest to study in detail. The search continues, using multiple techniques and instruments, as astronomers work to determine whether this ancient wanderer travels alone or has planetary companions. Red dwarf stars, like Barnard's star, present interesting challenges for the possibility of life. They're prone to stellar flares, sudden eruptions of energy, and charged particles that could harm any life on nearby planets. They also emit most of their energy in the infrared, meaning any photosynthetic life would need to adapt to harvest energy from infrared light rather than visible light, as plants do on Earth. The habitable zone around a red dwarf is much closer to the star than Earth's orbit around the Sun, raising the possibility that planets in this zone might become tidally locked, with one side always facing the star. Yet despite these challenges, red dwarfs are the most common type of star in the galaxy, and they live for trillions of years, offering vast amounts of time for life to emerge and evolve. If life can adapt to the conditions around red dwarfs, then the galaxy could be teeming with living worlds, as most stars are red dwarfs like Barnard's star. The star's name honors E. Barnard, an American astronomer who measured its large proper motion in 1916. Barnard was a pioneering observational astronomer who made numerous discoveries, and this fastest-moving star serves as his astronomical memorial, still bearing his name more than a century after his discovery. As we contemplate Barnard's star, we're reminded of the dynamic nature of the cosmos. Stars are not fixed points in space, but travelers on long journeys through the galaxy. They approach each other and drift apart over thousands and millions of years, their positions in the sky constantly shifting, though usually too slowly for us to notice. Barnard's star, with its rapid motion, makes this cosmic dynamism visible, a reminder that the universe is not static but constantly changing, constantly in motion. This ancient red dwarf, racing through our neighborhood, possibly accompanied by worlds of its own, represents both the commonplace and the mysterious. It's one of the most common types of stars, yet we still have much to learn about it. It's close enough to study in detail, yet it keeps its secrets, leaving us to wonder whether planets orbit in its faint red glow, and whether any of those worlds might harbor life adapted to conditions vastly different from those on Earth. Our journey continues to Wolf 359, a faint red dwarf lurking 7.86 light-years from Earth, in the constellation Leo. This small star exemplifies the most common type of stellar object in our galaxy, yet it remained unknown to humanity until the 20th century, hidden by its incredible dimness, despite being one of our nearest neighbors. Wolf 359 takes its name from Max Wolf, a German astronomer who catalogued it in 1919 as the 359th entry in his catalogue of stars with high proper motion. The star's official designation reflects its discovery through patient astronomical surveys, rather than through ancient observations of the night sky. No ancient astronomer ever saw Wolf 359. No classical civilization told stories about it, because it's simply too faint for human eyes to detect without optical aid. This tiny star is one of the smallest and least massive stars known. It has only about 9% of our Sun's mass and roughly 16% of the Sun's radius. It's barely large enough to sustain hydrogen fusion in its core, the fundamental process that defines a star. Any smaller and it would be a brown dwarf, a failed star that never achieved the conditions necessary for sustained fusion, glowing only with the heat of its formation and slowly cooling over billions of years. The surface temperature of Wolf 359 is approximately 2800 Kelvin, making it one of the coolest stars we know. This low temperature gives it a deep red color, though most of its energy output is actually in the infrared, invisible to our eyes. The star produces only about 0.1% of the Sun's luminosity, or about 1,000th as much light. Despite being less than 8 light-years away, Wolf 359 has an apparent magnitude of 13.5, meaning you would need a decent amateur telescope to observe it at all. Wolf 359 is what astronomers classify as a flare star, a type of variable star that experiences sudden dramatic increases in brightness. These stellar flares are caused by magnetic activity on the star's surface, similar to solar flares on our Sun, but proportionally much more powerful. During a flare, Wolf 359 can briefly increase in brightness by several magnitudes, potentially doubling or even tripling its normal luminosity for a few minutes before fading back to its usual dim state. These flares release enormous amounts of energy, including ultraviolet radiation, X-rays, and charged particles. For any planet, orbiting close to Wolf 359. These flares would present a significant challenge to the development and maintenance of life. The radiation could strip away atmospheric gases over time, and the bursts of high-energy particles could damage biological molecules and DNA. Any life around such a star would need robust protective mechanisms, whether that's a strong magnetic field to deflect charged particles, or living underground or underwater to shield from radiation. The star moves through space at a considerable velocity relative to our Sun, with a proper motion of about 4.7 arcseconds per year, making it the sixth fastest moving star visible from Earth. Like Barnard's star, Wolf 359 is currently approaching our solar system, though at a much slower rate. It will reach its closest approach in about 13,000 years, when it will be roughly 7.68 light-years away, only slightly closer than its current distance. Wolf 359 is estimated to be several billion years old, though precise ages for red dwarf stars are notoriously difficult to determine. These stars change very slowly over time, maintaining nearly the same size, temperature, and luminosity for trillions of years. Unlike more massive stars that evolve through distinct stages of their life cycle, red dwarfs simply burn steadily for time periods that exceed the current age of the universe by factors of hundreds or thousands. This incredible longevity means that Wolf 359 will still be shining when our Sun has long since exhausted its fuel, expanded into a red giant, and finally collapsed into a white dwarf. When the universe is hundreds of billions of years old, when most of the larger stars have burned out and only the red dwarfs remain, Wolf 359 will still be fusing hydrogen, still glowing in the darkness, a testament to the efficiency of the smallest stars. Searches for planets around Wolf 359 have so far come up empty, though this doesn't definitively mean the star has no planets. Detecting planets around such dim stars is extremely challenging, as the techniques astronomers use to find exoplanets all rely on detecting tiny changes in the light from the star, whether that's the slight dimming as a planet transits across the star's face, or the subtle wobble induced by a planet's gravitational pull. With such little light to work with, and with the complications introduced by the star's flare activity, any planets around Wolf 359 would be particularly difficult to detect. Yet the absence of confirmed planets doesn't mean they're not there. Many red dwarfs are known to host planets, some rocky and Earth-sized, some larger and more like Neptune. The habitable zone around Wolf 359, where liquid water could exist on a planet's surface, would be very close to the star, perhaps only a few million miles away, far closer than Mercury is to our Sun. At this distance, a planet would likely be tidally locked, with one hemisphere always facing the star and the other in perpetual darkness. Despite its proximity and the astronomical attention paid to nearby stars, Wolf 359 remains enigmatic. It's a star that reminds us how much we still have to learn about even our closest neighbors. Each red dwarf is unique, with its own patterns of flare activity, its own rotation rate, its own magnetic field structure. Understanding these stars in detail requires patient observation over long periods, as their subtle changes play out over years and decades. Wolf 359 gained a certain cultural notoriety through its appearance in science fiction, particularly in the Star Trek universe, where it was the site of a famous battle. This fictional fame stands in interesting contrast to the star's actual nature, a dim, solitary ember, too faint for ancient astronomers to see, discovered only through systematic surveys, interesting primarily to specialists in stellar astronomy. Yet in that contrast lies something worth reflecting upon: how our imaginations can take even the most obscure astronomical objects and weave them into stories, making them meaningful in ways that transcend their physical properties. As we contemplate Wolf 359, we're reminded that our galaxy is filled with stars like this one, small red dwarfs that collectively make up the majority of the stellar population. They're the background stars, the common citizens of the galactic community, each one a sun in its own right, but too small and dim to draw much individual attention. Yet they may also be the most common homes for planets, and potentially for life. Their long lifetimes, offering vast expanses of time for evolution to work its slow magic. Our next stellar neighbor, Lalande 21,185, awaits us at a distance of 8.29 light-years from Earth. This red dwarf star, situated in the constellation Ursa Major, the Great Bear, has been known to astronomers for over 2 centuries, yet it continues to reveal new secrets as our observational capabilities improve. The star's name comes from the French astronomer J.R.M. Lalande, who included it in his famous star catalogue published in the early 1800s. The number 21,185 simply indicates its position in this comprehensive catalogue. This naming convention might seem impersonal compared to the evocative names of stars like Sirius or Betelgeuse, but it reflects the systematic approach of astronomical surveys that have catalogued millions of stars, most of which must be identified by numbers rather than unique names. Lalande 21,185 is slightly larger and more massive than Wolf 359, with about 14% of the Sun's mass and approximately 23% of the Sun's radius. Its surface temperature is around 3,400 Kelvin, somewhat warmer than Wolf 359, but still significantly cooler than our Sun. It emits about 2.2% of the Sun's luminosity, making it substantially brighter than Wolf 359, though still far too faint to see with the naked eye. You would need binoculars or a small telescope to observe this nearby star. Like many of our closest stellar neighbors, Lalande 21,185 is moving rapidly through space, from our perspective, with a proper motion of about 4.8 arcseconds per year, very similar to Wolf 359's motion. The star is approaching our solar system and will continue to do so for approximately 20,000 years, eventually reaching a minimum distance of about 4.65 light-years around the year 21,000 CE. At that point, it will briefly be one of the 3 closest stars to our Sun before beginning its recession into the farther reaches of the galaxy. Lalande 21,185 has been the subject of extensive searches for planetary companions. As one of our nearest neighbors, it represents a prime target for planet hunting efforts, and over the years there have been several claimed detections of planets in this system. However, many of these early claims turned out to be spurious, artifacts of stellar activity or observational limitations, rather than true planetary signals. The star is classified as a B, Wide Draconis variable, a type of variable star that shows small amplitude changes in brightness due to large star spots on its surface, rotating in and out of view. These star spots are similar in principle to sunspots on our Sun, but proportionally much larger, sometimes covering significant fractions of the star's visible surface. As the star rotates, taking about 12 days to complete one rotation, these spots create periodic variations in the star's brightness. This stellar activity complicates the search for planets. The same spots and the magnetic activity that creates them can produce signals that mimic the presence of planets, leading to false detections. Distinguishing between stellar activity and genuine planetary signals requires careful analysis and multiple independent observations using different techniques. Despite these challenges, evidence suggests that Lalande 21,185 likely does host at least 2 planets, though their properties remain somewhat uncertain pending additional observations. If confirmed, these worlds would orbit close to their star, bathed in the dim red glow of a red dwarf sun, experiencing conditions vastly different from those on Earth. The potential for life around stars, like Lalande 21185, remains an open question. The star is more active than our Sun, with frequent flares and strong magnetic activity that could pose challenges for life. However, its relative brightness compared to other nearby red dwarfs, like Wolf 359, might provide a more stable environment. The habitable zone around Lalande 21185 would extend from about 0.2 to 0.4 astronomical units from the star, a distance similar to Mercury's orbit around our Sun. Any planet in this habitable zone would complete an orbit in just a few weeks or months, experiencing seasons on timescales completely foreign to Earth's year-long cycle. The star would appear significantly larger in the sky than our Sun appears from Earth, a red disk that would dominate the heavens of any orbiting world. The age of Lalande 21185 is estimated to be around 5 to 6 billion years, making it slightly older than our Sun. This means that if planets formed around this star early in its history, they would have had sufficient time for life to potentially emerge and evolve to complex forms. Of course, we have no evidence for life in this system, but the possibility remains intriguing given the star's age and potential for hosting rocky planets. Lalande 21185 serves as a good example of why astronomers pay such close attention to nearby stars. At just over 8 light-years away, this star is close enough that detailed observations are feasible with current technology. Any planets in this system would be among the easiest exoplanets to study, potentially allowing astronomers to analyze their atmospheres for biosignatures, molecules that might indicate the presence of life. The star also illustrates the patient, incremental nature astronomical research. Lalande 21185 has been observed regularly for over a century, with each generation of astronomers using the best tools available to them. Early observations simply tracked its position and motion. Mid-20th century observations measured its spectrum and studied its variability. Modern observations search for planets and characterize the star's activity in detail. This accumulation of data over decades and centuries allows astronomers to understand these objects more completely. Looking at Lalande 21185 from Earth, you would find it in the constellation Ursa Major, not far from the familiar pattern of the Big Dipper. While the bright stars of the Big Dipper are easy to locate and have been used for navigation for thousands of years, Lalande 21185 hides among the fainter stars, invisible to the naked eye, a reminder that the universe contains far more than what we can see. Without technological assistance, this red dwarf, like so many of its kind, represents both the ordinary and the profound. It's one of countless billions of similar stars in our galaxy, yet it's unique in its details, its history, its planetary system if it has one. It's close enough to study yet far enough to require our best efforts to understand. It's ancient, yet will outlive everything we know by incomprehensible stretches of time. As we contemplate this star, 8 light-years away in the darkness, we're reminded of the vastness of our cosmic neighborhood and the richness it contains. Each nearby star is a world unto itself, with its own story, its own characteristics, its own potential for hosting life. Lalande 21185 is just one chapter in the grand story of our local stellar environment, but it's a chapter worth reading, full of mysteries yet to be fully solved. Now we arrive at one of the most famous stars in the night sky, Sirius, the brilliant jewel of the constellation Canis Major. At 8.6 light-years from Earth, Sirius is not our absolute closest neighbor, but it's by far the brightest star we can see in Earth's night sky, a beacon that has captured human attention since the dawn of civilization. The name Sirius comes from ancient Greek, derived from the word meaning glowing or scorching, a fitting name for this intensely bright star. The ancient Egyptians called it Sopdet and based their calendar on its heliacal rising, the moment each year when the star first became visible in the dawn sky, after a period of being too close to the sun to observe. This rising coincided with the annual flooding of the Nile River, a crucial event in Egyptian agriculture, making Sirius one of the most important stars in Egyptian astronomy and culture. The Romans knew Sirius as the dog star because of its position in Canis Major, the constellation representing one of Orion the hunter's dogs. They believed that when Sirius rose with the sun during the hottest part of summer, it added its heat to the sun's, creating the oppressively hot dog days of summer. While we now know that distant stars don't affect Earth's weather, the term dog days persists in our language, a linguistic fossil from ancient astronomy. Sirius is actually a binary star system consisting of two stars orbiting their common center of mass. The primary star, Sirius A, is a white main sequence star about twice as massive as our Sun and approximately 25 times more luminous. With a surface temperature of about 9,940 Kelvin, significantly hotter than our Sun's 5,800 Kelvin, Sirius shines with a brilliant white light that has a subtle blue tint. The reason Sirius appears so bright in our sky is a combination of its intrinsic luminosity and its relative proximity. While it's 25 times more luminous than our Sun, it's also much closer than most of the other bright stars we see. If you could move Sirius to the same distance as some of the truly luminous stars visible in our sky, stars like Rigel or Deneb, it would fade to invisibility. Conversely, if you move those distant supergiants to Sirius's distance, they would blaze like small moons in our night sky. The companion star, Sirius B, is one of the most fascinating objects in our stellar neighborhood. It's a white dwarf, the dense remnant core of a star that has exhausted its nuclear fuel, expelled its outer layers, and collapsed to a fraction of its former size. Sirius B packs about 98% of the Sun's mass into a sphere only about the size of Earth. This extreme density creates a surface gravity about 350,000 times stronger than Earth's surface gravity. White dwarfs represent the fate of medium-sized stars like our Sun. When these stars exhaust the hydrogen in their cores, they expand into red giants, then shed their outer layers, leaving behind their hot cores. These cores, no longer generating energy through fusion, slowly cool over billions of years, eventually fading to become black dwarfs, theoretical objects that the universe isn't yet old enough to have produced. Sirius B is one of the nearest white dwarfs to Earth, making it an important object for studying this final stage of stellar evolution. It has a surface temperature of about 25,000 Kelvin, much hotter than Sirius A, but because of its tiny size, it produces only about 2.5% as much light as its larger companion. The contrast in brightness between the two stars makes Sirius B challenging to observe, as it's lost in the glare of brilliant Sirius A when viewed through telescopes. The two stars orbit each other every 50 years at an average separation of about 20 astronomical units, roughly the distance from our Sun to the planet Uranus. The orbit is quite elliptical, with the stars ranging from 8 to 31 astronomical units apart as they swing around each other. The most recent closest approach occurred in 1994, and the next will happen in 2044. The discovery of Sirius B is a fascinating chapter in astronomical history. In 1844, the mathematician Friedrich Bessel analyzed precise measurements of Sirius A's position and noticed that it wobbled slightly, suggesting the presence of an unseen companion. This companion was finally observed directly in 1862 by the telescope maker Alvan Graham Clark. The discovery was significant because it demonstrated that careful positional astronomy could reveal invisible stellar companions, a technique that would later be applied to the search for exoplanets. When Sirius B was first studied spectroscopically, astronomers were puzzled. Its spectrum indicated a hot, white star, suggesting it should be luminous. Yet it was faint, implying it was small. The realization that a star could be both hot and faint led to important insights about stellar structure and the existence of white dwarfs, fundamentally changing our understanding of stellar evolution. From a planetary perspective, any planet orbiting in the Sirius system would need to orbit one star or the other, rather than both together, as the two stars come too close to allow stable orbits in the region between them. A planet orbiting Sirius A, at a distance where liquid water could exist, would need to orbit at about 3 times Earth's distance from the Sun, taking several years to complete one orbit. Such a planet would experience complex lighting conditions, with the bright primary star providing most of the light and heat, while the faint white dwarf Sirius B would appear as an intensely bright star, far brighter than any star in Earth's sky, but still not bright enough to provide significant warmth. No planets have been detected in the Sirius system, and it's unclear whether planets could survive the evolution of Sirius B from a main sequence star to a red giant and finally to a white dwarf. The expansion phase would likely have consumed any inner planets, while the mass loss from the star might have destabilized the orbits of outer planets. However, second-generation planets could potentially form from the debris disk created when Sirius B shed its outer layers. Sirius has featured prominently in human culture across many civilizations. The ancient Greeks associated it with the heat of summer. Indigenous Australian peoples have various traditions involving the star, some seeing it as the footprint of a celestial bird. The Polynesians use Sirius as a navigational aid in their ocean voyages. In Chinese astronomy, Sirius was known as the celestial jackal. This star has been observed and interpreted by every human culture that could see it, making it one of the most culturally significant celestial objects. The system is approaching our solar system at a velocity of about 5.5 kilometers per second, though it will not make a particularly close approach. In about 64,000 years, it will reach its closest distance to our Sun, about 7.86 light-years away, briefly appearing even brighter than it does now, before beginning to recede again. Sirius reminds us that stars exist in different stages of their life cycles. Sirius A is in the prime of stellar life, steadily fusing hydrogen into helium. Sirius B has already completed its main sequence lifetime and now slowly cools, its fusion fires extinguished. Together, they show us both the present and future, active stellar life and post-fusion quiescence, blazing brightness and fading ember. At a distance of 8.73 light-years, we encounter Luyten 726-8, another binary star system, but this one consists of 2 red dwarf stars that orbit each other in a close cosmic partnership. These 2 small stars, designated UV Ceti and BL Ceti, are so similar in size and brightness that they're nearly twins, bound together by gravity in a system that will persist for trillions of years. The system is named after Willem Jacob Luyten, a Dutch-American astronomer who catalogued it as entry 726-8 in his extensive survey of nearby stars with high proper motion. The individual stars are also known by their variable star designations, UV Ceti and BL Ceti, referring to their locations in the constellation Cetus, the whale or sea monster. UV Ceti, the slightly larger of the two, has about 12% of the Sun's mass, while BL Ceti has approximately 11% of the Sun's mass. Both stars are significantly smaller than the Sun, with diameters only about 14 to 15% of the solar diameter. Their surface temperatures are around 3000 Kelvin, giving them deep red colors, though as with other red dwarfs, most of their energy output is in the infrared rather than visible light. The 2 stars orbit each other at a separation of about 2.1 astronomical units, roughly twice the distance from Earth to the Sun, completing one orbit every 26.5 years. Despite this relatively close orbital spacing, each star maintains its own identity, and the system is clearly resolved as two separate stars when viewed through telescopes, unlike some binary systems where the stars orbit so closely that they appear as a single point of light. What makes UV-CT particularly famous in astronomical circles is that it's the prototype for an entire class of variable stars called UV-CT variables, or flare stars. UV-CT itself undergoes dramatic flares, sudden eruptions where the star can brighten by an entire magnitude or more within seconds, becoming several times more luminous than its normal state, before fading back to its usual brightness over the course of minutes to hours. These flares are caused by intense magnetic activity on the star's surface. The magnetic field lines become twisted and tangled by the star's rotation and internal dynamics until they suddenly snap and reconfigure, releasing enormous amounts of energy in the process. The result is a burst of light across the electromagnetic spectrum, from radio waves through visible light and into X-rays and even gamma rays. During these flares, the radiation output from UV-CT increases dramatically, not just in visible light, but especially in ultraviolet and X-ray wavelengths. For any planet orbiting close to such a star, these flares would represent significant hazards. The bursts of high-energy radiation could damage or destroy atmospheric molecules, particularly ozone layers, that protect surface life from ultraviolet radiation. The charged particles accelerated by these flares could interact with planetary magnetic fields, creating powerful auroras and potentially affecting any electronics on the planet's surface. BLCT also exhibits flare activity, though perhaps not quite as dramatically as its companion. The two stars likely have similar magnetic activity cycles, though they vary independently. The flare behavior of both stars has been studied extensively over the decades, providing insights into the magnetic dynamos operating inside red dwarf stars and the processes that generate stellar flares. The system moves through space at a considerable velocity relative to our Sun, with a proper motion of about 3.4 arcseconds per year. Currently, Luyten 726-8 is moving away from our solar system, gradually increasing its distance from us. It was closer in the past and will be more distant in the future, a reminder of the ever-changing configuration of our stellar neighborhood. No planets have been confirmed around either UV-CT or BL-SETI, though their proximity and the attention they receive make them good targets for planet searches. Detecting planets around flare stars is particularly challenging because the flare activity can mask or mimic planetary signals. The brightness variations caused by flares can be confused with the transits of planets passing in front of the star, and the magnetic activity can create spectral variations similar to those caused by orbiting planets. Nevertheless, if planets do exist in this system, they would experience fascinating and challenging conditions. The star's habitable zones would be very close in, probably less than 0.2 astronomical units from each star. At this distance, planets would be tidally locked, with one hemisphere always facing their star. The combination of tidal locking and flare activity would create extreme environments, with one side baked by constant stellar radiation and frequently bombarded by flares, while the other side remained in perpetual frozen darkness. Yet life, if it arose in such an environment, might find ways to adapt. Organisms might live underground or underwater, shielded from the most intense radiation. They might develop rapid DNA repair mechanisms to cope with radiation damage. They might be most active during the star's quiescent periods between flares, retreating to shelter when activity increases. Life on Earth has adapted to environments from deep-sea vents to Antarctic ice, demonstrating remarkable resilience and flexibility. life around flare stars might develop similar adaptations to their challenging environments. The two stars in the Lewitton 726-8 system offer an interesting comparison with our Sun. Each star is roughly 1/8 the mass of our Sun, meaning that together they total about 1/4 of the Sun's mass. Yet their combined luminosity is less than 1% of the Sun's luminosity. This dramatic difference illustrates how stellar luminosity scales with mass. Small decreases in stellar mass lead to large decreases in luminosity. This relationship is why red dwarfs, despite being the most common stars in the galaxy, contribute relatively little to the total light output of the galaxy. These stars will live for trillions of years, far longer than the current age of the universe. They burn their hydrogen fuel so slowly that they will still be shining long after all the larger stars, including our Sun, have exhausted their fuel and died. In the far future, when the universe is cold and dark, when star formation has ceased because all the available gas has been consumed, red dwarf stars like UV-Ceti and BR-Ceti will be among the last remaining beacons of light, slowly cooling over incomprehensible stretches of time. As we contemplate this binary system, we're reminded of the diversity of stellar configurations in our neighborhood. Some stars, like our Sun and Barnard star, travel alone. Others, like Alpha Centauri and Lewitton 726-8, travel in pairs. Some pairs consist of similar stars, like UV and BR-Ceti, while others, like Sirius, pair dramatically different stars together. Each configuration creates unique environments and challenges for planet formation and the potential development of life. Our journey brings us to Ross 154, a red dwarf star, located 9.69 light-years away in the constellation Sagittarius. This star is another entry from a systematic astronomical catalogue, specifically the catalogue compiled by Frank Elmore Ross in the early 20th century. Ross was an astronomer who specialized in surveying nearby stars, and his catalogue includes many of the closest stars to our Sun. Ross 154 is a solitary star. Unlike some of the binary and multiple systems we've encountered, it drifts through space alone, without stellar companions, though it may have planets that accompany it on its journey through the galaxy. This stellar solitude is actually less common than we might think. Most stars in the galaxy are members of binary or multiple systems, making single stars like our Sun and Ross 154 somewhat exceptional. With about 17% of the Sun's mass and roughly 20% of the Sun's radius, Ross 154 is slightly larger than some of the other red dwarfs we've visited, though still much smaller than our Sun. Its surface temperature is approximately 3,200 Kelvin, and it produces about 0.5% of the Sun's luminosity. As with other nearby red dwarfs, it's too faint to see with the naked eye, requiring a telescope to observe. Ross 154 is classified as a B wide Draconis variable, the same type of variable star as Lalande 21185. It shows periodic variations in brightness caused by large star spots rotating in and out of view as the star spins. These brightness variations are relatively subtle, typically less than half a magnitude, but they're measurable and have been studied extensively. The star rotates every 287 days, unusually fast for a red dwarf, and this rapid rotation likely contributes to its strong magnetic activity and the formation of large star spots. Like many nearby stars, Ross 154 has a substantial proper motion, moving across our sky at about 0.67 arcseconds per year. It's currently moving toward our solar system and will continue to approach for the next several thousand years. In about 157,000 years, Ross 154 will reach its closest approach to our Sun, when it will be only about 6.4 light-years away, making it one of the closest stars to our solar system during that epoch. After that closest approach, it will begin receding, eventually leaving our immediate neighborhood entirely. The star also has a significant radial velocity, the component of its motion either toward us or away from us along our line of sight. It's approaching us at about 10 kilometers per second, contributing to the overall decrease in distance over time. This combination of tangential motion across the sky and radial motion toward or away from us determines the star's complete trajectory through space relative to our solar system. Ross 154 has been searched for planetary companions, but so far, no planets have been confirmed around this star. The searches continue as improved instrumentation and techniques make it possible to detect smaller and more distant planets. The habitable zone around Ross 154, where liquid water could exist on a planet's surface, would be quite close to the star, perhaps 0.15 to 0.25 astronomical units away, similar to other red dwarfs we've discussed. The age of Ross 154 is uncertain, as with many red dwarfs. These stars are difficult to age date because they change so slowly over time. Current estimates suggest the star is probably several billion years old enough that any planets around it would have had time for significant geological and potentially biological evolution. One interesting aspect of Ross 154 is its metallicity, the astronomical term for the abundance of elements heavier than hydrogen and helium. Ross 154 appears to have a lower metallicity than our Sun, meaning it contains fewer heavy elements. This could have implications for planet formation, as planets, particularly rocky planets, require heavy elements to form. Lower metallicity stars might be less likely to host large terrestrial planets, though the relationship between stellar metallicity and planet formation is still an active area of research. The star emits most of its energy in the infrared portion of the spectrum, like other red dwarfs. This has interesting implications for photosynthesis if plant-like life were to evolve on any planets in the system. Photosynthesis on Earth has evolved to use the visible light that our Sun produces most abundantly. Around a red dwarf like Ross 154, photosynthetic organisms would need to adapt to harvest energy from infrared light, possibly requiring different pigments and biochemical pathways than terrestrial plants use. Ross 154's rapid rotation and magnetic activity make it an interesting object for studying stellar magnetic fields. The magnetic field of a red dwarf, generated by the motion of conducting plasma inside the star, can be quite strong and complex. These fields channel the stellar wind, create star spots, and generate flares. Understanding red dwarf magnetism helps astronomers understand not only the stars themselves, but also the environments around them, including the space weather that any planets would experience. From a planet orbiting Ross 154, the star would appear as a large red disk in the sky, much larger than our Sun appears from Earth, because any planet in the habitable zone would orbit much closer to this smaller, dimmer star. The star spots on the surface would be visible as darker regions on the stellar disk, rotating across the face of the star every few days. The sky might have a perpetual sunset appearance, with the red light of the star creating a different visual environment than we experience on Earth. Despite being one of our nearer neighbors, Ross 154 remains relatively unstudied compared to some of the other stars we've visited. It's not as close as the Alpha Centauri system or Barnard star, not as famous as Sirius, and not as dramatic in its variability as UV Ceti. Yet it represents the typical stellar citizen of our galaxy, a medium-small red dwarf, probably several billion years old, possibly hosting planets, slowly burning its hydrogen fuel in a process that will continue for trillions of years. As we contemplate Ross 154, nearly 10 light-years away, we're reminded that space exploration is not just about the dramatic discoveries and the famous objects. It's also about the patient work of cataloging and studying even the unremarkable stars, building up a complete picture of our cosmic neighborhood. Each star, no matter how ordinary it might seem, contributes to our understanding of stellar populations, galactic structure, and the potential distribution of planets and life throughout the universe. Continuing outward from our Sun, we arrive at Ross 248, also known by its variable star designation HH Andromedae, located 10.29 light-years away in the constellation Andromedae. This red dwarf is another catalogue entry from Frank Elmore Ross's systematic survey of nearby stars, and like Ross 154, it provides insights into the common red dwarf stars that populate our galactic neighborhood. Ross 248 has about 14% of the Sun's mass and approximately 16% of the Sun's radius, making it somewhat smaller than Ross 154. Its surface temperature is around 3,200 Kelvin, similar to other red dwarfs we've encountered, and it produces only about 0.4% of the Sun's luminosity. As with nearly all the stars we're visiting tonight, Ross 248 is too faint to see without optical aid, hidden among the much brighter stars that dominate our night sky. The star is another example of a By Draconis variable, showing periodic brightness variations due to rotating star spots on its surface. These variations are small but measurable, and they've been monitored over the years to track the star's rotation period and magnetic activity level. The rotational period of Ross 248 is about 150 days, much slower than Ross 154's rapid 2.87-day rotation. This slower rotation suggests that Ross 248 may be an older star, as red dwarfs gradually spin down over time due to magnetic braking, the loss of angular momentum through the stellar wind. What makes Ross 248 particularly interesting from a long-term perspective is its motion through space. The star has one of the higher proper motions of any nearby star, moving across the sky at about 1.6 arcseconds per year. More significantly, it's approaching our solar system at a considerable velocity. In approximately 38,000 years, Ross 248 will become the closest star to our Sun, overtaking even Proxima Centauri for a period of time. At its closest approach, it will be only about 2 light-years away, about 29% closer than Proxima Centauri is now. This closest approach will be temporary, lasting a few thousand years before Ross 248 continues on its path and recedes from our neighborhood, eventually to be replaced by some other star as the nearest neighbor to our Sun. This changing configuration of nearby stars reminds us that the stellar neighborhood we see today is just a snapshot in time. Over tens of thousands of years, the cast of characters in our immediate vicinity changes as stars move past each other on their respective orbits around the galactic center. Ross 248 is estimated to be approximately 1.6 billion years old based on its activity level and rotation rate. Though as with all red dwarf ages, this estimate comes with significant uncertainty. If this age estimate is correct, Ross 248 is considerably younger than our Sun, which is 4.6 billion years old. This younger age might explain its relatively high activity level and the presence of star spots on its surface. Like many nearby red dwarfs, Ross 248 has been searched for planets, but no confirmed planetary companions have been discovered yet. The searches continue with ever-improving sensitivity. The habitable zone around Ross 248 would be located very close to the star, within about 0.15 astronomical units, far closer than Mercury's orbit around our Sun. At this distance, any planet would orbit Ross 248 in just a few weeks and would almost certainly be tidally locked to its star. The stellar wind from Ross 248 the stream of charged particles flowing outward from the star, would be substantially different from our Sun's solar wind. Red dwarfs generally have stronger magnetic fields relative to their size than larger stars, and these fields shape and channel the stellar wind. For planets in close orbits around red dwarfs, the stellar wind and the magnetic interaction between star and planet can be important factors in atmospheric retention and evolution. One interesting aspect of Ross 248 is its X-ray emission. The star has been observed in X-rays by various space telescopes, revealing that despite its low total luminosity, it's quite active in high-energy radiation. This X-ray emission comes from the hot plasma in the star's outer atmosphere, heated to millions of degrees by magnetic activity. For any close-in planets, this X-ray radiation would represent an additional environmental challenge, potentially affecting atmospheric chemistry and the possibility of life. Ross 248's eventual status as our nearest stellar neighbor, albeit temporarily, raises interesting possibilities for future space exploration. By the time Ross 248 becomes our closest neighbor, 38,000 years from now, humanity will either be long gone or will have advanced technologically to the point where interstellar travel might be possible. If the latter is true, Ross 248 might become the first destination for interstellar probes or even crewed missions, simply by virtue of being the closest target available. The star's motion through the galaxy follows an orbit that takes it around the galactic center every 225 million years or so, similar to our Sun's orbital period. Sometimes its orbit brings it close to other stars and stellar systems. Sometimes it travels through regions of space where stars are more sparse. Currently, it's passing through our neighborhood, a brief visit in the context of galactic timescales, long enough to be noticeable on human historical timescales, but momentary in the life of the star itself. From a hypothetical planet orbiting Ross 248, the view of the cosmos would be somewhat different from the view from Earth. The constellations would be recognizable, but slightly shifted due to the different vantage point. Our Sun would be visible as a bright yellow-white star, perhaps among the brightest stars in their sky. A reminder that our ordinary Sun is actually quite luminous compared to the numerous red dwarf stars that fill the galaxy. Ross 248 exemplifies the gradual accumulation of astronomical knowledge. When first catalogued by Ross, it was simply one more entry in a survey of faint nearby stars. Over the decades, astronomers have measured its spectrum, its variability, its motion through space, and its high-energy emission. They've searched for planets and studied its magnetic activity. Each observation adds another small piece to our understanding of this particular star and of red dwarfs in general. As we consider this future nearest neighbor to our Sun, we're reminded of the dynamic nature of stellar positions. The stars we see in the night sky are not fixed in place, but constantly moving, usually too slowly for us to notice, but inexorably shifting over thousands and millions of years. The neighborhood we inhabit is temporary, a particular arrangement of stars that happens to exist in this era. In the past, the arrangement was different, and in the future, it will be different again. Our final destination brings us to Epsilon Eridani, located 10.48 light-years away in the constellation Eridanus, the river. Unlike most of the stars we've visited tonight, Epsilon Eridani is visible to the naked eye from Earth, though just barely. It appears as a faint star in the southern constellation, unspectacular to casual observers, but fascinating to astronomers who recognize it as one of our closest stellar neighbors. Epsilon Eridani is a K-type main-sequence star, sometimes called an orange dwarf. It's smaller and cooler than our Sun, but larger and brighter than the red dwarfs that have dominated our journey. With about 82% of the Sun's mass and 74% of the Sun's radius, Epsilon Eridani is a mid-sized star representing a middle ground between the numerous but tiny red dwarfs and the less common but more massive stars like our Sun. The surface temperature of Epsilon Eridani is approximately 5,100 Kelvin, noticeably cooler than our Sun's 5,800 Kelvin, giving the star its characteristic orange hue. It produces about 34% of the Sun's luminosity, making it the most luminous star in our local neighborhood after Sirius. This relative brightness, combined with its proximity, makes it the third brightest star within 10 light-years of Earth. What makes Epsilon Eridani particularly exciting is that it's a young star by stellar standards, with an age estimated at only 400 to 800 million years. This makes it less than 1/5 the age of our Sun. The star is still in the early stages of its main sequence lifetime, a stellar youngster, compared to the ancient red dwarfs we've encountered. This youth has important implications for planet formation and the potential for life. Epsilon Eridani hosts a confirmed planetary system, one of the closest exoplanetary systems to Earth. The star is surrounded by large disks of dust and debris, similar to but much more extensive than the asteroid belt and Kuiper belt in our own solar system. These disks reveal themselves through infrared observations, as dust warmed by the star's radiation glows in infrared light. The most notable planet in the system is Epsilon Eridani b, a gas giant with at least 0.78 times the mass of Jupiter. This planet orbits its star at a distance of about 3.5 astronomical units, taking approximately 7 years to complete one orbit. This places it somewhat farther from its star than Mars is from our Sun, in a region where ice and rock can accumulate to form large planets. The existence of Epsilon Eridani b has been confirmed through multiple techniques, including radial velocity measurements that detect the wobble the planet induces in its star's motion. The planet's mass and orbit suggest it's similar to Jupiter, likely a gas giant with no solid surface, composed primarily of hydrogen and helium, with perhaps a rocky or icy core deep within. There's evidence for at least one additional planet in the system, possibly orbiting closer to the star, though this inner planet has not yet been definitively confirmed. The multiple dust belts and the presence of at least one gas giant suggest that Epsilon Eridani could host a diverse planetary system, possibly including smaller rocky planets in addition to the confirmed gas giant. The dust belts around Epsilon Eridani are particularly interesting. They indicate ongoing processes of planetary formation and evolution. Dust is constantly being removed from the system through radiation pressure and other forces, so the presence of so much dust suggests that it's being replenished, probably through collisions between asteroids and comets. This is similar to the situation in our early solar system, when Earth and the other terrestrial planets were still forming and the inner solar system was a chaotic place filled with colliding planetesimals. The youth of Epsilon Eridani means that its planetary system is still evolving. If terrestrial planets exist in the inner system, they might still be experiencing heavy bombardment from asteroids and comets, similar to the late heavy bombardment that Earth experienced about 4 billion years ago. These impacts would make the surfaces of such planets hostile environments, though they would also deliver water and organic molecules that could later support life once conditions stabilized. From a planet orbiting in the habitable zone of Epsilon Eridani, roughly 0.61 to 0.85 astronomical units from the star, the sky would feature the orange sun providing warmth and light. The debris disks might be visible as faint bands of light crossing the sky, similar to zodiacal light seen from Earth, but more prominent. Any gas giant planets would be visible as bright stars or even small disks, depending on their positions in their orbits. Epsilon Eridani is more active than our Sun, producing stellar flares and showing signs of strong magnetic activity. This is partly a result of its youth, as young stars tend to be more active than older ones. The star rotates relatively quickly, completing one rotation every 11 days, compared to our Sun's 27-day rotation period. This rapid rotation helps generate a strong magnetic dynamo in the star's interior, leading to enhanced activity. The increased stellar activity might pose challenges for life on any planets in the system. Frequent flares release bursts of ultraviolet radiation and charged particles that could damage or erode planetary atmospheres. However, if a planet has a strong magnetic field, as Earth does, it could deflect much of this hazardous radiation, protecting the surface and any life that might exist there. The proximity of Epsilon Eridani and the presence of a known planetary system make it a prime target for detailed study. As telescope technology improves, astronomers hope to directly image planets in the system, analyze their atmospheres, and search for biosignatures that might indicate the presence of life. If we're going to find life around nearby stars, Epsilon Eridani is one of the best candidates, combining proximity with the confirmed presence of planets. The star has featured prominently in science fiction, often imagined as the home of advanced civilizations or the destination for humanity's first interstellar colony. This fictional fame reflects its real-world characteristics. It's close, it's visible from Earth, it has planets, and it's young enough that we can imagine its planetary system still developing and evolving. Epsilon Eridani will remain on the main sequence, stably fusing hydrogen into helium, for another 20 billion years or more. During this immense span of time, its planetary system will continue to evolve. The debris disks will gradually clear as material is either accreted onto planets or ejected from the system. If terrestrial planets exist in the habitable zone, they'll have billions of years for life to emerge, evolve, and potentially develop intelligence. By the time Epsilon Eridani exhausts its fuel and begins to die, civilizations could have risen and fallen on its worlds. Empires could have come and gone, all under the light of the orange sun. As our final stop on this journey through our stellar neighborhood, Epsilon Eridani reminds us of the diversity and potential of planetary systems. Each star we visited tonight offers different possibilities. Ancient red dwarfs that will burn for trillions of years. Binary systems where twin suns dominate alien skies. Young stars surrounded by forming planets. Dead stars that have already exhausted their fuel. Together, these stars paint a picture of the varied stellar landscape in our corner of the galaxy, hinting at the even greater diversity that exists among the hundreds of billions of stars throughout the Milky Way. Our journey through the nearest stars to our Sun comes to an end, but the exploration of our cosmic neighborhood continues. Tonight, we've traveled across light years of space, visiting 10 of the closest stellar systems to our solar system. Each one unique, each one a world unto itself. We've seen that our local neighborhood is dominated by red dwarf stars, those small, cool, long-lived embers that make up the majority of the stellar population, not just in our vicinity, but throughout the galaxy. Proxima Centauri, Wolf 359, Lalonde 21185, UV Ceti and BL Ceti, Ross 154, Ross 248. These red dwarfs will outlive virtually every other type of star, burning their hydrogen fuel so slowly that they'll still be shining when the universe is hundreds of billions or even trillions of years old. Yet our neighborhood also contains diversity. Alpha Centauri offers us a glimpse of sun-like stars, yellow and orange companions locked in an orbital dance. Sirius shows us both a brilliant main sequence star in its prime and a white dwarf, the dense remnant of a star that has already completed its life cycle. Epsilon Eridani presents us with a young stellar system still in formation, with planets and debris disks evolving before our telescopes. The distances we've discussed tonight, from just over 4 light-years to slightly more than 10, represent the nearest stellar systems we can study. Yet even these closest neighbors are separated from us by gulfs of space so vast that light, traveling at 186,282 miles per second, takes years to cross them. The fastest spacecraft we've built would require thousands of years to reach even the nearest stars. The distances between stars are truly immense, emphasizing both our isolation and our uniqueness. Yet we're not as isolated as we might feel. The light from these stars reaches us every night, photons that began their journey years ago, carrying information about distant suns. Our telescopes collect this light, our spectrographs analyze it, and our computers process the data, allowing us to study these stars in remarkable detail, despite never having visited them. We know their temperatures, their compositions, their motions through space. We've detected planets around some of them and searched for planets around others. We've watched their flares, measured their rotation periods, and tracked their paths through the galaxy. The question of life beyond Earth hangs over all these observations. Could any of these stellar systems host living worlds? We don't know yet, but the possibilities are tantalizing. Proxima Centauri b orbits in its star's habitable zone. The Alpha Centauri system could host Earth-like worlds. Epsilon Eridani's planetary system is still forming, perhaps developing terrestrial planets even now. The ancient red dwarfs have had billions of years for life to emerge and evolve on any planets they might possess. Life, if it exists on worlds around these stars, would likely be adapted to conditions vastly different from those on Earth. It might harvest energy from infrared light rather than visible light. It might shelter underground or underwater to escape stellar flares. It might have evolved under the light of a red sun that hangs motionless in the sky of a tidally locked world. The diversity of stellar environments suggests that if life has emerged in any of these systems, it would show us new and surprising forms, expanding our understanding of biology beyond the single example we know on Earth. The stars we've visited tonight have been observed by humans for varying lengths of time. Sirius has been known since prehistory, featuring in the mythology and calendars of ancient civilizations. Epsilon Eridani is faintly visible to the naked eye and appears on traditional star charts. But most of our stellar neighbors remained unknown until systematic astronomical surveys in the 19th and 20th centuries revealed their existence. Many are so faint that despite being closer than famous distant stars, they went unnoticed for most of human history. This reminds us that our perception of the universe is limited by our senses and our technology. The brightest stars in our night sky are often the most distant, luminous giants and supergiants that shine across hundreds or thousands of light years. Meanwhile, our actual neighbors, the stars that share our region of the galaxy, are mostly too faint to see without telescopes. Reality and appearance diverge. The universe is not as it seems to casual observation. As we develop better telescopes and more sophisticated detection methods, our knowledge of these nearby stars continues to grow. Each year brings new discoveries, new planets, new insights into stellar activity, refined measurements of stellar properties. The catalogue of our stellar neighborhood becomes more complete and more detailed with each passing year. Looking to the future, these nearest stars represent humanity's first potential destinations for interstellar travel. Various proposals have been suggested for robotic probes that could reach the nearest stars within decades using advanced propulsion methods. Concepts like laser-pushed light sails or fusion rockets might make interstellar travel feasible within this century. The nearest stars might receive visits from robotic explorers from Earth within the lifetimes of people alive today. Crude interstellar travel remains far more challenging, requiring either journey times of thousands of years in generation ships or breakthrough propulsion technologies that currently exist only in theoretical discussions. Yet what seems impossible today may become achievable in the future as technological capabilities advance. Humanity might one day establish a presence around some of these stars, expanding beyond our home system to become a truly interstellar species. The stars we've visited tonight are moving through the galaxy on their own paths, sometimes approaching our solar system, sometimes receding. The stellar neighborhood we know today is temporary, a particular configuration that happens to exist in this era. Proxima Centauri is currently our nearest neighbor, but in 38,000 years, Ross 248 will take that title. In 157,000 years, Ross 154 will be among our closest neighbors. The cast of characters in our immediate vicinity changes over tens of thousands of years, reminding us that the universe is dynamic, constantly in motion, forever changing. Our Sun is just one star among hundreds of billions in the Milky Way galaxy. The 10 stellar systems we've explored tonight represent just a tiny sample of our immediate galactic neighborhood. Beyond them lie countless more stars, stretching across the galaxy and beyond into the vast universe. Each is a sun in its own right, each potentially hosting planets, each possibly home to worlds where life has emerged and evolved. As you drift towards sleep, imagine the darkness of space, punctuated by the distant glow of stars. Picture Proxima Centauri's dim red light, Alpha Centauri's binary brilliance, the blazing white of Sirius, the flaring variability of UV Ceti. These are our neighbors in the cosmic city of the Milky Way, fellow travelers on the long journey around the galactic center, companions sharing this corner of space and time. The universe is vast beyond comprehension, yet we've been able to reach out with our technology and our intelligence to study even distant objects, building a picture of the cosmos through careful observation and patient analysis. We are connected to the stars, not just through the atoms in our bodies, forged in ancient stellar furnaces, but through our ability to study them, to understand them, to appreciate their beauty and significance. The stars we've visited tonight will continue their journeys through the galaxy long after humanity has either spread among them or ceased to exist. They represent something eternal in a universe where most things are temporary, something grand in a cosmos that dwarfs our everyday concerns. They remind us of our place in the universe, small but significant, brief but meaningful, isolated but part of a greater whole. As you close your eyes, let your mind drift among the stars. Feel the immensity of space and time, the slow wheeling of galaxies, the patient burning of stellar fires. Know that above you, whether hidden by daylight or visible in the darkness, the nearest stars continue their ancient dance, glowing as they have for billions of years, as they will for billions of years, your trillions of years to come. The universe is patient. The stars are eternal. And we, for this brief moment, have the privilege of observing them, studying them, and appreciating our place among them. Sleep well under the light of distant suns.